start recording. All right. And we are going to go to Unit 0, and we're going to get started. Okay? What happens when stuff dissolves? Any of you guys familiar with Tyler DeWitt? If you're not, you will be by the end of this year. Although he kind of goes away for a large chunk of time in between the start of the year and the end of the year, because he doesn't really do anything with Chem 12 until we hit the end of the year. So we are on page 1 of Unit 0. Oh, organic chemistry tutor. Good person to know. Pardon me?
What happens when stuff dissolves?
Oh,
what happens to the atoms and molecules that make it up? I want to talk about two things here that you dissolve all the time. Salt and sugar. These two things look very similar. They're both like kind of white powders made up of little grains, and you can pour both of them into water and stir around, and you see the grains get smaller and
smaller. Yeah, I know. Okay, so let's make sure our sound is on. And we want this to be big. And we're going to go here. There we go. And hopefully this will look familiar to you from last year. Okay? Not necessarily this, but the process. Okay?
What happens when stuff dissolves? What happens to the atoms and molecules that make it up? I want to talk about two things here that you dissolve all the time. Salt and sugar. These two things look very similar. They're both like kind of white powders made up of little grains, and you can pour both of them into water and stir around, and you see the grains get smaller and smaller and maybe break apart until eventually they've totally disappeared. They've completely dissolved in the water. That's what you see with the naked eye. But if you had atomic vision and you could see the atoms that make up salt and sugar, what would it look like as these grains broke apart and became invisible? That's what we're going to talk about here. So it actually depends whether something is an ionic or a covalent compound.
And you guys right now are going to talk with your neighbors, and you are going to figure out, how do you know if something is an ionic compound or a covalent compound? You're going to describe that to your neighbor. If you and your neighbor don't know, you're going to go and find someone who does, because I am going to, in just a minute or two, call a name, a random name, to tell me how you know if something is, let's start with how you know if something is ionic, and then we'll do how you know if something is covalent. And if you don't know and your neighbors don't know, go find someone who does.
Look at it. You know what it is? Yeah, I know when it's just yes, I do. So ionic is literally just like a metal plus a non-metal, and it's the back positive. I need to remind us that field electron. That's how they make it ionic. So a covalent is two non-metals. They share. I remember still. Yeah. Oh, yeah.
Are we ready? Anyone need more time? Okay. Well, how do we know if something is ionic? Oh, and Gamby, how did you know? Has a metal, okay? If it has a metal, it is ionic. And it's not just going to have a metal. The formula is going to, or the name is going to start with a metal. Is there anything else an ionic compound can start with? There's one other thing it can start with. Hydrogen, hydrogen is weird because it will form molecular compounds or covalent compounds. Same word, molecular and covalent, those mean the same thing. But sometimes when we put hydrogen compounds into the water, they will dissociate into ions, but not all the time. Yeah, okay, so hydrogen compounds, acids, are a little bit weird, but we're going to spend a lot of time talking about them this year, so don't worry, we will clarify there. Anyone remember the other thing it can start with?
Like a diatomic.
Starts with an A.
Like the thing in the start, or like the thing in the end, I forgot. It's like sulfide or something. No, wait. That's something I know.
Okay, let's go. Why don't you go look in your data booklet on page 3 and see if you can find something that it might start with.
Yeah, I know.
Data booklet, page 3.
You know what? Oh, yeah. No, aluminium. No,
Starts with an A.
Oh, you're right.
Ammonium, yes. Okay, ammonium is a positive, what do we call those ions that contain more than one atom?
No, not diatomic.
Not diatomic, but polyatomic. These are our common polyatomic ions, okay? And at the top of the chart, we have our positive ions, our cations. Do you guys remember how to know that cations are positive? Because cats have pause, so cations are positive. Get it? I dare you to forget it now. Okay. Now, anions, there's lots of polyatomic anions. You can see we've got acetate, bromide is not polyatomic, carbonate, chlorate. Chloride is not polyatomic, chlorite, chromate, cyanide. How can you tell that cyanide is polyatomic and not just an element? What's that? You have 2 capital letters, which means there are 2 elements, okay? So it's got carbon and nitrogen, okay? All right, so there's our ions. And let's go back to our friend Tyler.
It depends on what it would look like when it dissolves.
Oh.
So over here we have salt.
Hang on. We didn't talk about how to tell if something is covalent. Everyone ready for covalent? Claire, how do you know if something is covalent? When they share electrons, yes. Okay, so covalent compounds share electrons. What types of elements share their electrons? Anyone want to try that? Or do I draw a card? Yes? Non-metals. So if you have a compound that is made exclusively of non-metals but doesn't start with ammonium, because ammonium, of course, is an ion. So if you have a compound that is exclusively non-metals, like this sugar here with 2 carbons, 4 hydrogens, and 2 oxygens, that is only non-metals, that is covalent. All right? And so now Tyler is going to share with us what happens when we dissolve ionic compounds versus covalent compounds.
And this is an ionic compound. This is what a grain of salt would look like, and it's made of sodium ions, Na+, which are metals, and Cl, chloride ions, these blue things here, which are nonmetals. So salt is an ionic compound made of metals and nonmetals. Sugar, on the other hand, is a covalent compound because it's made of nonmetals, carbon, oxygen, and hydrogen. And these nonmetal atoms are connected together into a molecule. So a grain of sugar would look like this. It would be a bunch of these sugar molecules all kind of lumped together. Notice that a grain of sugar is a lot more messy. It's not nearly as well organized as an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision, we're going to see that the atoms that make up this salt are going to come apart from each other.
He actually said something there that was a little bit incorrect. He said that the atoms that make up this salt are going to move apart from each other. Anyone know what's a little bit incorrect about that statement? Pardon me?
Molecules, probably not that.
Molecules, not atoms? No, but good guess. Okay. Are there any other particles? There's a little clue here and here.
What's their own? They cannot.
Sorry? Yes? Ions. Okay? They have charges, so they are ions. So it's not the atoms that are separating because they're not atoms. They have either gained or lost electrons, so they are ions with either a positive or negative charge.
Up this salt are going to come apart from each other. They're going to break apart and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay? Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up.
What's the difference between a molecule and an atom? Have a chat with your neighbor about that. What's the difference between a molecule and an atom? And I'm going to draw a card for that too. So be ready. Molecule and an atom.
I forgot. I remember like the only thing I'm thinking was literally thinking. I didn't know what you
Are we ready? Anyone not ready? Josh. Yes, okay, so what he said, for those of you who couldn't hear, he said that a molecule is when the atoms are compounded together, when they're stuck together. Did I get that right? Yeah, and then the atoms are when they're individual and separated, okay? But atoms have no charge, so they're different from ions, okay? Molecules also have no charge, and molecules are specifically for covalent compounds. Welcome back. Are you with us?
Our Lord and Savior has come.
Okay. And so anytime we do this little chit chat where I'm like, talk about blah, 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 if you have no idea, raise your hand and Taranya here will discuss with you. He's your like extra lab partner, okay?
But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms.
Ions.
So, to answer the question, what does it look like when something dissolves in water? The short answer is, it actually really depends whether you're talking about an ionic compound or a covalent compound. If it's an ionic compound, it's going to break apart into all of the individual atoms.
Ions.
But if it's a covalent compound, the clump of the molecules will break apart into individual molecules once it dissolves. But the molecules themselves will not break apart into atoms. They will stay as molecules dissolved in the water.
Okay, and we're going to pause there, and we are going to go and make sure we have filled everything in and just add a couple things that weren't there on the video. So Ionic was made of metal and non-metal, which I think most of you got, hopefully. So this is metal plus non-metal. What should we add here, though? We should add metal or what? Ammonium, NH4 plus ammonium. Okay, so that's your ionic. And covalent is made of only what? Only nonmetals. Watch out though, because if it starts with NH4, it is ionic. Careful. NH4NO3, those are all nonmetals. But it is ionic because it starts with ammonia. All right, and what the other thing we're going to do here is we are going to go through and we are going to put little pluses beside half of these. I know they all look gray on your page, I'm sorry, so you can just randomly choose which half you put pluses beside. And the other half we're going to put negatives beside. And we have freely floating ions. And ions have a charge. And I am really, really picky. If you write an ion and you do not write its charge, it is not correct. Okay, because if you write Na, that means you have a chunk of sodium metal, okay, with no charge. It has not lost any electrons, it's just neutral sodium. And if you throw it in water, it will catch on fire and eventually explode. Bang! Okay, it's quite exciting. But if you have sodium ions floating in water, they will not catch on fire, they will not explode, and you can use it to season your food. Yes? So there is a big difference between something that has already lost its electrons and something that has not lost its electrons. Okay, so our ionic compounds give us freely floating ions, whereas our covalent compounds give us freely floating molecules. And you're going to learn that I like to abbreviate things. I don't like writing out every single little thing. So MC stands for molecules. Okay, capital M, capital C stands for molecules. Because we can't have MOL stand for molecule because MOL stands for moles. Okay, so capital M, capital C is my abbreviation for molecules. All right. Now we can write the process of this ionic compound dissolving as it comes apart. Actually, why don't I grab us a anyone know what this is? Crystal lattice. Okay, this is a crystal lattice. This is how ionic compounds exist. They have alternating positive, negative, positive, negative, positive, negative. Now, this is a 1-to-1 crystal lattice. It's really hard to make a 2-to-1 crystal lattice. I don't know how you would draw it. I don't exactly know what it would look like. It would depend on the size of the ions. So we usually just simplify everything to a simple sodium chloride type salt where we just have positive, negative, positive, negative. And literally, when it goes into solution, you can imagine each of these individual ions coming off, okay? And that process where the two ions separate from one another is called dissociation. And the formula units separate into individual ions. Now, what the heck is a formula unit? Anyone know that term? Anyone familiar with that term at all? No? It's been a long time. It's okay. I know if you were in my class, we did use it, but you know, it has been a long time. A formula unit is a single unit of an ionic compound. So let's find a space where we can write this. A formula unit is a single unit, single unit of an ionic compound. It's almost like a molecule, but for an ionic compound. Okay? So here is a sugar molecule. That's a covalent compound. All the atoms stuck together are a molecule. If we had sodium chloride and we just had one sodium and we just had one chloride, that would be a formula unit. But you can never find that in nature. In nature, you have this three-dimensional structure called a crystal lattice. I'm not going to get too excited about that term right now. We'll talk more about it later. But we'll write it down anyway. This whole thing right here, this is called a crystal lattice. And that is in 2 dimensions, but this is what it would look like in 3 dimensions. And these can be big, they can be small. You can have a big salt crystal, you can have a small salt crystal. And that's why we don't really have a molecule, like this is not a molecule of salt, this is a crystal lattice of salts that could be big or it could be smaller. You could have more atoms, or sorry, more ions or less ions. But if we want to just refer to one of them, we call it a formula unit. If you call it a molecule, am I going to get mad at you? No, not really. But if you go off to university, you should probably know that it's not called a molecule for ionic compounds. It's called a crystal lattice, and a single unit is called a... Yes, it is called an ion, but what do we call those 2 ions together, the positive and the negative? We call that a formula unit. Everyone say it with me, a formula unit. Excellent. Okay. So we can write the dissociation. I would like you to say that word with me as well. Everyone, we're going to say it 1, 2, 3. Dissociation. Okay, dissociation is when the formula units split apart into individual ions, and we can write an equation for that. This is called a chemical equation. This is a dissociation equation. And the reason I distinguish that is because this is a chemical formula. Yeah, NaCl, that's a chemical formula. The equation is when we've got some reactants on one side of the arrow and some products on the other side of the arrow. That's an equation. Calcium chloride, I expect at this point you guys can all write your chemical formulas, and if not, I would sincerely hope that you consider dropping this course. Okay, if you cannot write chemical formulas just like that, either you're going to review them like crazy for the next day or so, or seriously consider dropping this course because it's just expected that you know that. You've been learning them since grade 9. Yes? Okay. So we have calcium chloride. Calcium, of course, is 2+. Chloride is is -1. And that's why we have CaCl2. That's what it is when it is a solid. When we dissolve it in water, it dissociates, it comes apart into the ions, and the ions are all separate from one another. So we have a calcium ion, and we have 2 chloride ions, and those 2 chloride ions are separate from one another. It's not a Cl2, it's just 2 Cls. We good with that? Okay, excellent. So that is dissociation. Dispersion. Dispersion is for what type of compounds? They are for covalent compounds. So dissociation is for ionic compounds. Why are you not moving, Paige? There we go. Dissociation is for ionic compounds. Dispersion, if I said to you, okay, class, disperse, what would you do? You would just run away and everyone would sort of go off in their own direction, yes? And that's what happens with these molecules. You've got a sugar crystal, that's all these sugar molecules stuck together, and we say disperse, and off they go. And that's basically what happens. So we have C12H22O11. This is sucrose, which is table sugar, and it's a solid. When it dissolves, its formula does not change because it does not come apart into individual atoms. So it is still exactly the same. The only thing that changes is its state. What is the state for dissolved in water? AQ, which stands for? Aqueous. Okay? AQ, dissolved in water, aqueous.
kind of like water and ice, like same formula, but like it's different.
Sorry, what was the question about how did ice come into it?
It's like water and ice, like
Water and ice are the same thing.
it's
They are
like-
both H2O.
Yeah, I know, but like it's just like one is aqueous and one is solid, right?
Ah, no. Aqueous literally means dissolved in water, so water cannot be dissolved in water. Yeah? So liquid water is liquid. Yes? So actually, it's interesting. In the last unit, we're going to be looking at the difference between liquid sodium chloride, where I would literally take this, heat it to 900 degrees Celsius, and melt it, no water present whatsoever, and that would be liquid. The ions would come apart and start flowing around, all like, yes? But there would be no water present, and that's called liquid, okay? When we take the salt and we dissolve it in water, the ions separate, but there is also water present. That is called aqueous, okay? So liquid is melted, aqueous is dissolved in water, okay? That's a really good point, okay? Are you guys familiar with the term intermolecular forces? No, okay. I'm going to just briefly mention them to you here. We're not going to get into big details around them, but intermolecular forces, do you guys know what the word the prefix inter means? Inter means between, yes. Inter is between. So if you have intermolecular, those are forces that are between molecules. So intermolecular forces are forces between molecules. Oh, and look at me, MCs, molecules, okay? So if I had some molecules, not that one, not that one.
Yeah,
I don't know what I've got. Okay. So many things. All right. Great. So here are some random molecules that I made for my Chem 11 Enriched class a few years ago. Okay, so we've got a molecule here, we've got a molecule here, molecule, okay, and
what are those flat things called? I actually forgot.
those flat things, those are lone pairs of electrons. Okay, so we got our lone pairs of electrons here. And there are going to be some positive areas on here, and there's going to be some negative areas on each of these molecules. And the positive and negative areas will, what do positive and negative do to one another? They cancel out, but they also attract. Okay? And so there are attractive forces. They are not as strong as bonds. Okay, so a covalent bond, an ionic bond are much, much stronger. Okay? But if I were to take this, let's just pretend these are all sugar molecules. I know they all look different, but I don't have a bunch of sugar molecules on hand. Let's pretend these are all sugar molecules. When I dump them into water, the forces holding them together are broken. Okay? And so we are breaking those intermolecular forces. All right? Now, it turns out there's new intermolecular forces because the water that goes around it now attracts the molecules. Okay? So there's new intermolecular forces between this molecule and the surrounding water. Okay? But that's about it. Yes? You good with that? Okay. So intermolecular forces, that's what they are. They're simply forces between what? Forces between molecules, and they are weaker than bonds. Weaker than bonds. Is any of this going to be on your test? No. So you're like, why am I learning it? Because it is foundational to everything that we do in this course. If you don't understand these things, you cannot do Chemistry 12. And I notice there are some people falling asleep. So we're all going to stand up. Everybody stand up. Because I don't know how you all sit here all day. Like I go to a staff meeting and I have to be there for an hour and a half and I think you can die. I'm like, oh my God, it's so horrible. Where is my stool? There it is. Okay, we are going to stretch. Oh my God, I'm being blinded. I need to turn that thing off. Okay. Okay, we're going to stretch up high. And then we're going to go over to our left. And then we're going to go over to our right. Oh. Then we're going to go forward a little bit, back a little bit. We're going to do some windmills. Don't hit your neighbor. I'm sorry, this is not very practical for you. Yeah. And now we are going to do the no neck pump exercise. Because when you get to my age, if you spend all day doing this, I don't know if you guys can see it, but there's like a little hump there. And it makes me very, very upset and unhappy. And you don't want this. And you spend more time doing this than I do. Yes? So what we're going to do is we are going to stand up straight. Okay? You might want to like spread yourselves out a little bit because your arms are going to be out like this. So give yourself enough room that your arms are out to the side. You don't have to participate, but it's good for you. Okay? And what you're going to do is you are going to, actually, we're going to curl our fingers like that and curl our fingers like that. And we're going to point our thumbs forward. And then we're going to pinch our shoulders together in the back. Okay, and now we're going to go do circles forward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And now we're going to flip our thumbs backwards. And we're going to go backwards and we're going to do 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And now you're going to shake out your arms. Oh, shake out your shoulders. And now we're going to sit down and we're going to finish the lesson. Okay?
I need that.
And you can build up from there. When I do them, I usually do like 60 in either direction, so I do it for like 1 minute each, yeah. But we'll start with 20, okay? All right, so we are going to actually now skip ahead to page 11. Page 11. Yes.
Dissociation particle diagram.
So these are dissociation particle diagrams because most of the compounds we will be dealing with in Chemistry 12 are ionic compounds, unless they are acids or bases, although bases are actually ionic compounds as well. So you need to be able to write dissociation equations. We're actually working our way. By tomorrow, we will be looking at net ionic equations, complete ionic equations, formula equations. How many people remember those words? How many people remember how to do them? A few of you? Okay, if you do remember, that's fantastic. If you don't, no worries, we will review them, okay? But we want to be done by tomorrow, yes? Okay, so for each of the following salts, what we are going to do is we are going to write the dissociation equation. We are going to identify the ratio of the particles, whether it's 2 to 1, 1 to 1, whatever. And we are going to draw the ions present in the correct ratios. And we're going to look at the first one is done for us as an example. So our first thing here we have is NaNO3. And I would like to point out to you that this little 3 here does not mean that we have 3 NOs. Okay? There's not 3 NOs because NO3 is the nitrate ion, and it is a group that looks like this. NO, O, O. Yeah, there's 3 oxygens, 1 nitrogen. The whole thing has a negative charge. Okay, there's not 3 of them, there's just 1 of them. All right. So when we take this, we have 1 sodium and we have 1 NO3. So when we dissolve it in water, when we take our solid and we dissolve it in water, the 2 ions, what do? They, what's the word?
Dissociate.
Dissociate. Everyone say it? Dissociate. So we end up with a sodium ion and a nitrate ion, and they are present in a 1-to-1 ratio. So we have written the dissociation equation. And then we're going to draw the ions. And there should be 1 sodium for every 1 nitrate. And you don't have to write the N and the O. You don't have to draw them like that. So we would have, here we have 1, 2, 3, 4 sodiums, and we have 1, 2, 3, 4 nitrates. If I were to have used 3 sodiums, I would use how many nitrates? 3. Polyatomic ions act as a single unit. They stay intact. Okay? In the exercises, you do not have to draw the solid, but this is what the solid sodium chloride would look like. That's our sodium nitrate would look like. That's our crystal lattice. You don't need to draw it. And then we'll have an example where we have a non-1-to-1 ratio. We've got K2S. What is the name of this compound? Tell your neighbor. K2S. That is indeed potassium sulfide. Yes. How many Ks are there? 2. So when they dissociate, we're going to put our 2 here, okay? And because it is dissolved in water, the state is now aqueous. So when we do our dissociation equation, we have to write that it's aqueous. We also have to make sure that we write the charge, the plus or the minus, okay? So when you do these, you need to have the coefficient, you need to have the charge, all right? And the sulfide, S, of course, needs a 2 minus, and you need its state, which is aqueous, dissolved in water. Not melted, but dissolved in water. All right, and there is our lovely potassium sulfide crystal lattice. That's our solid. We take it, we dissolve it in the water, and for every 1 sulfide you get 2 Ks. That was interesting. And so we have 1, 2, 3, 4, 5, 6 Ks, and we have 3 S's. All right. The exact number of ions you draw in the solution is not important as long as the ratio is correct. So if you're like, I don't want to draw 6 Ks, I'd rather only draw 4 Ks, you can just have like 4 Ks and 2 S's. Okay. We don't need this to be a big project for you. All right. Common errors when writing dissociation equations. We've already talked about these. You absolutely must write the ions charge, okay? You must write aqueous, all right? And when MgCl2 separates, when it dissociates, Is our second product Cl2 aqueous? Well,
I think it should be. Wait, no. It's in the formula sheet, right?
yeah. You might think that it's Cl2 because chlorine is one of the diatomic elements, but wait. This chlorine is not in its elemental state. It is not on its own. It is part of a compound. Yes? So if we look at our Lewis structures, are you guys familiar with Lewis structures? Yes? And if you're not, you're going to be familiar with them now. Here is a neutral chlorine atom. Chlorine is in group 17. So if you recall, that means it has 7 valence electrons. What are valence electrons?
The outer shell.
They're electrons in the outer shell. Okay, so it has 7 valence electrons, so we draw 7 dots around the chlorine. Now, if we have elemental chlorine, tell your partner, what does it mean to have elemental chlorine?
Pure chlorine.
Pure chlorine, not part of the compound, yes. How many valence electrons do atoms want in order to be happy? They want to be full. Yes, they're not going to be happy. We should actually, instead of saying happy, we should say, anyone remember? Starts with an S. Stable, not sad, stable. Okay, stable is a full octet, a complete 8 electrons. Okay, this is stable. Each chlorine has a full octet, which is 8 electrons. So this chlorine on the left shares one of its electrons with this chlorine on the right. And when they both share, then this chlorine has 8 electrons. And this chlorine has 8 electrons. And I don't know if you remember, but in Lewis structures, we can represent the shared electrons. Instead of using dots, we can use a line. That is a pair of shared electrons. That is a covalent bond. And that is natural, neutral, elemental chlorine. That chlorine has no charge. 0 charge. But if chlorine, instead of being on its own, if it is with magnesium, magnesium says, hey, I need to be stable, and I'm in group 2. If I'm in group 2, how many valence electrons do I have? 2. Okay, so here's magnesium. It's got 2 valence electrons. And remember, chlorine is in group 17, so it has 7 valence electrons. And so it's got an empty spot here. Each of those chlorines have an empty spot. and magnesium says, I will give away one of my electrons to one of the chlorines, that will give chlorine 8 electrons, and it becomes chloride, the negative ion. The second chlorine takes that second electron, it becomes another chloride ion with 8 electrons. Does this look to be the same structure as that? Are those the same things? No, okay? Cl2 is Cl2 when it is elemental chlorine, just like F2 or O2. Those are all when they're elemental, when they're not in a compound. When they are ions, those chlorides are separate from one another. So it's not Cl2. When you separate them, they come apart as 2Cl minus. So like we had back here, do you remember we had K2S? And the Ks all came apart separately from one another? That's what chlorides do. They come apart separately from one another, just like the Ks did, okay? All right, so for homework, what you guys are going to do is you are going to do Unit 0, pages 13 and 14. And because this is grade 12 and it just never stops, okay, you are going to do Unit 1, your green book. You can see stuff on your own. Oh, yeah, I know.
I love reading books.
Green book, you're going to read, watch. Now, when I say watch, what that means is that, do you see how there's a QR code? That's a video. You're going to watch that video, okay? And it tells you how long it is. It is 3 minutes and 3 seconds long. Do you think you can handle it?
No.
Then, so you're going to read what it says in here. You're going to watch the little video. And then at the bottom, it says, read Hubden, pages 1 and 2, and do number 2, do page 2, numbers 1 through 5. Okay, so read and watch pages, let's see, page 1.
We watch all of this like for
In unit, yeah. Actually, let's do pages 1 and 2.
Oh.
1 and 2.
1 and 2?
Yes. Yes. Maybe more. Okay, so if you don't like it and you're like, I don't like this and I'm not going into sciences, this would be your time to walk away. Okay, just letting you know, it will not work out well if you don't do homework regularly. And this includes Habden. No, Hebden is not optional. Pages 1 to 2, read, and do numbers 1 to 5 on page 2. This actually isn't that much, okay? Honest to God, the 3 videos, there's a 47-second video, there's a 40-second video, and there is a 6-minute and 21-second video. Like, honestly, this is not going to take you any more than an hour at the very, very outside. Yes? So we got Unit 1, Unit 0, Unit 1, Hebden. There we go. Would anyone like to sign out a copy of Hebden? Yes? Meet me over there. I'll grab you a book card. So if you would like a Hebden, meet me over at the bookshelf.
I can just open up my tablet. Oh, well, I finished my math already, so I can only work on chemistry today. I know. Yeah, we're all too smart for you. We're all too smart. Genius, you know. Yeah, I know. That is, we're all too lazy. Like the ice is like